Alright, let's talk about rocket science for a little while. The basic idea here is that we have a system of changing mass. That is the kind of big picture issue. And so the idea would be that conservation of mass says that, initial momentum equals final momentum, then, mi vi should equal mf vf. So, mass goes down, velocity goes up, basically. That is more or less the big picture. However, it's somewhat more complicated than this. So let us start here. So this is what we're looking at. You have a rocket, and that's what this is. Rocket has mass m, rocket and fuel, I guess, traveling at speed v. Later on, we have a rocket that has ejected the fuel. So the fuel has been ejected at a speed u in this reference frame. That's relative to the frame, not relative to the rocket. So that is the speed of the fuel, just straight up. The mass of the rocket, keep in mind, still our rocket, mass of the rocket has now been decreased by dm, and the speed of the rocket has been increased by dv. And so now we're using dm and dv to mean, basically a little mass and a little velocity. The idea is that this is a continuous process. It's always happening. So we're not like pushing off a giant chunk of mass. We're saying, all right, I have ejected a little bit of mass, and this is going to increase my speed by a little bit of an amount. That is where calculus starts to play nice with this. So, looking at our initial state. In our initial state, we are basically looking at the mass of the rocket times the velocity of the rocket. Nothing complicated. In our final state, we now have the mass of the fuel times the velocity of the fuel plus the mass of the rocket, which is now decreased, times the velocity of the rocket, which is now increased. So that's conservation of momentum. We'll find how many different ways I can abbreviate that as time goes on. Alright. This is, again, nothing too terrifying yet. So, what the book wants to do is it wants to introduce this relative velocity. And this is the velocity of the rocket relative to product. So if we think about this, remember that we had way back yonder when we were talking about velocity, we said that if I wanted the velocity of A relative to B, that looked like the velocity of, oh god, hold on, A relative, whatever, plus B relative to C was A relative to C. So if I know how far the person is moving relative to the train, and how fast the train is moving relative to the ground, I know how fast the person is moving relative to the ground. And ground does not start with R like relative does. So, in this case, what we're looking at, we want the velocity of the... So we have the velocity of the rocket relative to the frame. And we have the velocity of the fuel relative to the frame. Frame also does not start with R. And so the piece that we're missing is the velocity of the rocket relative to the fuel. Still does not start with R. Relative to the fuel. This is what we are going to call V relative. So this is basically a measure of what the ejected rate of the fuel is. How fast you're pushing the fuel back. If you're pushing the fuel back fast enough such that the fuel goes backwards, you are going to take off like a light. If you're just kind of tossing the fuel out so that it's still going forward at something just slightly less than the rocket speed, your gain is not as great. But the point is, this is kind of the quantity that's controllable. So, why do we do this? What does this mean? This means that V is equal to U plus V relative. right? Right. More specifically, this means that v plus dv, because that's the speed of the rocket once it's been accelerated and u is in the play. So, yes, yes, no, yes, yes. All right, sorry. There's a sign difference in the text, and I always get a little fuzzy on it. So we can define u then as v plus dv minus v relative. So what does that get us? If we go up back to our equation now, we have mv, just gonna bring this down so that I can actually look at it, dmu plus m minus dm v plus dv. You may notice at this point I changed a sign relative to the book because they make dm negative for some reason that doesn't really make me happy. Alright, mv is equal to, although I may come to remember why they do it, v plus dv minus v rel plus, let's see, we'll go m v plus dv minus dm v plus dv. So we're just going to distribute this onto that, which I realize is not the most descriptive of things. And so if we distribute this dm also, we see that this term and this term gonna cancel. So now we are looking at something like this. mv equal to minus dm v relative plus mv plus dv. So that looks positively messy, but wait, if we distribute this in, we see that we have mv plus mdv, mv on both sides, which I guess I can actually take the 3 seconds to write, which is going to cancel. And so we wind up with something that looks a little like this. We have minus dm by m is equal to dv by v relative. Alright. Which is interesting. Now, they decide to take, your book takes a slightly different take. So my instinct here would be to integrate this, and we would get the log of both sides, and that's probably, or, now we're going to get something weird if we do it that way. What your book does instead is they say, alright, so we have minus dm, oops, hold on, this should not be minus, that should be positive. Minus signs, they'll come for you. So we have dm v relative equal to mdv. And they're going to take a time derivative of both sides. Kind of. So they're going to say we can just do this. And you know, that's kind of possible, sort of. I mean, it's basically turning these into time rates. And we'll just go with it. So we have dm by dt v rel equal to m dv dt. And so this dm dt, your book says, is basically r, which is the rate of mass loss. And in my case, r is, alright, so they make r the positive rate of fuel consumption. In my case, it is the negative rate of mass consumption. It's the negative rate of fuel, of mass change. So, you know, that's funky, but whatever. It's the rate of fuel consumption, basically. In my mind, should be a negative number, but, you know, whatever. We'll deal with that later. Times v rel is equal to m, and then dv dt, our old standby, is a. So this is what your book calls the first rocket equation. And what it has done for us, it said, alright, if we look at this, it says that ma which is shockingly enough then, Newton's second law here, is equal to R times V relative. So the faster we burn fuel and the faster we eject it, gets us more thrust. So we're going faster. Not the most shocking of consequences, but kind of nice to get there. Now, the question that we might want to ask is, where do we go from here? Well, from this, let's go back to this statement. So we were saying that we have this nice little differential equation. It looks like something we can probably integrate by parts. Not integrate by parts, separate. So we'll bring this thing on down. And so we had, I really should remember this maybe, dm by m equals dv by vrel. So keep in mind, wow, that's a terrible looking m. This is just a constant. So we'll rearrange this, say dm by m times vrel is equal to dv. If I integrate both sides, I'm going to get something that looks like log m times vrel is equal to v. I'm going to have some kind of constant here. So we're probably going to have to do this from some initial velocity to some final velocity, and some initial mass to some final mass. So that would get us something that looks like this. If I do the integrals. And this is what they call then the second rocket equation. So what does this bind us? This says, so if we take, for example, the case that VI is 0, and if VF were to, for example, equal escape velocity, which we'll get to later, then I have some number based on my rocket, which is going to tell me V relative. This is going to tell me what kind of ratio I need for the initial fuel to the final fuel. I'm off by a minus sign. Where is that minus sign coming from? Now do I care that this is a negative number? Oh, right. So dm is technically a decrease. So this order should be switched. Because I should be going from... Yeah, there's a minus sign. Minus signs of the devil. dm is technically a negative number. Or a negative quantity. Because I had a decrease of mass. But I don't know how I feel about that. Because it wasn't a negative number, it was a positive number. Why should that... I'll come back to this. Remind me about it. That minus sign should come out somewhere naturally, and I'm just not seeing it right now. But anyway, the point is this would tell you kind of roughly how much fuel you need. So if you're not going to wind up empty, I guess. Or maybe you could go with the limit that you wind up empty, but it's, yeah. Anyway, back to the beginning. The important bit of this for our perspective is kind of this analysis up here of talking about, an differential change in something's momentum. You can think of this in terms of if you wanted discrete events of like throwing ping pong balls or like launching something off the back of a rocket to try to make yourself fly faster. And this is basically just the continuous case of that. And this is it's a nice example of kind of how calculus buys you something a little fancier than you started with. So hopefully this is an interesting little excursion. I don't know that I necessarily made it any better than the book did. I largely copied what they did, but hopefully the narrative helps. It's not essential to kind of the study of this. I mean, it's not going to come up on the AP exam. It's probably not going to come up on our quizzes or anything. But it is, you have to admit, rocket science has its charm. So, enjoy.